In this video, we'll talk about logistic function. First, let's look at its graph. So for this function, we have t and p, where t is time and p is the amount by the time t. You can see in this graph, there's an upper limit L. So the maximum value won't pass this maximum value L. That's the upper limit. And the rate of change is kind of slow at the beginning. It's right here. It's like going up a little bit. And then the rate of change is going a lot more. And then it's decreasing, gradually decreasing. And then as bigger the t is, the slope is closer to 0. Right? And this is the equation for this logistic function, where L is the upper limit and K is the growth rate. The logistic function is used in many different fields. For example, like population growth with limited resources. First, the population will grow kind of slow, and then when everyone get used to the environment, the growth rate is growing, the growth rate is faster, and then as the resources run out, the growth slow down again. Another application would be the learning curves that also follows the logistic function model. If you learn a skill at the beginning, it's hard, and then you grow faster. The skills will improve quickly after a period of time, and then it starts to slow down as you approach your potential. And the derivative of this function p is equal to k times p times L minus p. So k we know is the growth rate, right? P is the amount you have at the moment, and L minus p, you can see that as the potential of growth. The rate of change of the amount is proportion to the amount itself and the space to grow. Now let's look at this word problem. Suppose that a company introduces a new computer game in a city using television advertisements. Surveys show that P% of the target audience buy the game after X ads are broadcast, satisfying the equation below. Answer the questions. Okay, question A. What percentage buy the game without seeing a TV ad, which is when X is equal to 0? So that's easy. Let's just find what is P of 0. Right? Plugging is 0 in the function. That's 100 divided by 1 plus 50 times e to the negative 0.12 times 0. That's 100 divided by 1 plus 50 times, e here is to the 0. That's just 1, right? So 100 divided by 51, whatever that value is, and that value is 1.96 something. So if you round it with 1 decimal place, that's 2.0, right? So how do you answer question A? About 2% of the target population will buy the game without seeing any ads. Okay, now part B, what percentage buy the game after the ads runs 26 times? That's also easy. That's P of 26, right? Just plug in 26 into the function. If I round the answer to the nearest tenth, that will be 31.2. So what does it mean? That means about 31.2% of the population, target population, will buy the game after the ads run 26 times. Okay, part C, find the rate of change, the derivative of p of x. Here I would just take the derivative, but of course you can use the formula given to us. You can say dp dx is equal to k times p times l minus p here, right? You have to figure out what k is or what l is. Just go back to the formula, you can figure out what those values is, and then you have to plug in here. But I think it's a little bit easier just to do the derivative, so I'm going to just do that, do the calculation. So here I can see it as 100 times 1 plus 50 e to the negative 0.12x. This whole denominator to the negative 1 power. So if I take derivative of that, that will be 100 times negative 1, then over that part squared, 1 plus 50 e to the negative 0.12x squared, and then chain rule, right? Take the derivative of this part. That would be 50 times e to the negative 0.12x, another chain rule, times times another negative 0.12. Okay, simplify everything a little bit. Negative and negative cancel out. So on top, 100 times 50 times 0.12, that's 600. Times e to the negative 0.12x all over the bottom part. Just write it down. Right? That'll be the derivative of p, the rate of change. Last part, sketch a graph of the function. Okay, so obviously this is a logistic function, and we know the graph roughly look like an S, right? So with x over here and p of x over here, and then the graph, there's a maximum value or upper bound, that will be the 100, that will be our L, right? So this is your, let's make it dots because it's not part of the graph. This is our L, and we calculated the p of 0 earlier. That's what our y-intercept, that's 2%, so it's around 2. Let's say it's here, and the graph, it will look like an S, so it's like kind of like this. So this is how the graph roughly look like.